All right, this is Electrochemistry Part II. Part 1, we learned how to balance redox reactions in an acidic and basic solution and did a little bit of review of oxidation numbers and oxidation states. And now we're going to apply that information to real world examples of electrochemical cells. So electrical chemical cells are conversions of chemical energy into electrical energy. There's the voltaic cell, or also called the galvanic cell. Voltaic or galvanic. Galvanic is an older term that represents cells where spontaneous reactions occur, and that's something like a car battery or a lithium-ion battery. Those are spontaneous reactions. And then the other type of electrochemical cell is an electrolytic cell. An electrolytic cell is a non-spontaneous reaction in the forward direction, but can be made spontaneous with the addition of electrical energy. Think of recharging your lithium-ion battery. So lithium-ion battery is a voltaic cell as it discharges and powers your phone, and then you plug it into the wall and it becomes an electrolytic cell as it recharges. So let's talk about what oxidation reduction looks like. So in the diagram on the left, or the photo, we have a piece of zinc metal, and we have it in a copper 2 ion solution. Again, remember that 2 represents the charge. And so this reaction is spontaneous. And so if you leave the zinc in the copper 2 positive ion solution, if you look on the atomic scale, zinc ions on the metal electrode or just the metal sheet, if you want to call it that, are being converted into zinc 2 positive ions. So that's oxidation. Zinc is being oxidized to zinc 2 positive. So zinc's a solid. Zinc 2 positive is an ion in solution. And so zinc actually looks like it's disappearing, but actually it's just being dissolved into the solution. On the other hand, the copper is in solution. It's a copper 2 positive ion. It's why it's blue. All right. And over here you see that the blue is lightening up. And so what's happening there is the copper 2 positive ion is gaining electrons and becoming copper solid. So this black substance you see deposited on the zinc electrode is actually copper. So you say, why is it black? Well, it can look kind of reddish, it can look black, and so but that is the copper metal being deposited on the zinc. So in this reaction, we're not getting any work out of it, right? This is happening right at the interface of the metal strip and the solution, and this reaction is happening spontaneously. So we know that delta G ought to be negative for this reaction for it to be spontaneous. So what we want to do is we want to get work out of this. We want to get some work done. And so we want to use those electrons for work. So let's define some things. Electric current is the amount of electric charge that passes through a point at a given time. So we're looking at flow of electrons through a cross section in a given amount of time. Redox reactions, we have electrons that are released from the substance being oxidized. We have electrons going back into a substance that's being reduced. So we have a flow of electrons. And we know that delta G for spontaneous reactions has to be negative. And we know that voltaic or galvanic cells have to be spontaneous. So that's just a summary of what we're seeing in the previous slide. All right, so we want to keep the oxidation and reduction half reactions separate in an electrochemical cell, because we just saw if we put the metal strip in with the solution, the reaction happens spontaneously, but we're not getting any work out of the electrons. So in order to keep the two half reactions separate, we have to have a bridge between the two reactions, and that's called a salt bridge. So the salt bridge allows ions to flow through the two solutions that each half reaction is occurring without the reaction happening directly. So we're going to use electrodes. These electrodes is where the reactions happen, both at the oxidation site and the reduction site. And then we'll use a salt bridge to have the ability to shuttle electrons back and forth to complete a circuit, so to speak, in our electrochemical cell. All right, so here's a couple of definitions. These are really important. In an electrochemical cell, the anode is where oxidation occurs. It's where anions are attracted to it. So negative ions are attracted to the anode. They release electrons, and that's oxidation. So connected to the positive end of the battery in an electrolytic cell. All right. So oxidation, we symbolize the anode with a positive symbol because oxidation is occurring there, and the electrons are flowing out of that electrode. The cathode is where reduction occurs. The electrons are attaching themselves to something, and so positive ions are attracted to that electrode. Negative electrons are coming out, opposites attract, so positive ions are going to be attracted to that electrode. And it's symbolized by the negative end on a battery. All right? And so what you'll also notice is the cathode will gain weight. So just as the ion becomes a solid substance, it's going to deposit that metal onto the plate. And so the cathode generally gains mass as the reaction happens, and the anode generally loses mass. Now, where you might see this, if you have an electric water heater, you have an anode in that electric water heater so that the electrons that are flowing in the heating element don't degrade the tank itself, and so then if that happened, your tank would start leaking fairly quickly. So they put a sacrificial anode in your electric water heater, and it slowly loses weight because it's being dissolved, and eventually it can dissolve so much that then the electrolysis starts on the tank itself, or oxidation reduction, let's say that. And so then the tank will eventually crack open and then you get a new water heater. But some people will extend the life of the water heater by actually replacing the anode after so many years. So you can extend the life of a water heater by replacing the anode, and a lot of people don't know that. All right, so this is what I want you to visualize with an electrolytic cell. So let's talk about the components here. So this is one half reaction, and this is where another half reaction are happening. They have to be separate in order for us to get work out of it. So here's my salt bridge. So the salt bridge is generally some highly ionic substance, in this case potassium nitrate, and that dissolves in water so that we have positive and negative charge carriers, or positive and negative ions. We generally have some plugs here so that allow the ions to pass but not allow the salt to flow out of the bridge, the salt solution. So allows ions to pass but does not allow the potassium nitrate to flow out very easily. So generally these are made out of cotton. You can just use cotton plugs or something like that. Fritted ceramics, and that's a little fancier, but so either way, fritted just means little holes in a ceramic plate. All right, so here you have an electrode, here you have an electrode. They tell us that this is the anode, and they tell us that it's zinc. They tell us this is the cathode, and they tell us that that's made of copper. So the electrode is inserted into a solution of pota- of the electrode just it's submerged in a solution of zinc nitrate. All right. So we know that zinc nitrate completely dissolves in water, and if you don't know that zinc nitrate completely dissolves in water, then you need to go back and look at your solubility rules. So that's another thing you may want to brush up here. It doesn't hurt. So what happens here is the zinc, two positive, the zinc in the metal electrode is oxidized. So that's what happens. The zinc is oxidized into zinc 2 positive and 2 electrons are released. Again, oxidation. Oxidation occurs at the anode in a voltaic cell. All right. So the electrons are released. They flow through the wire. We get work out because what is force times distance? So the electrons go through the filament of the light bulb shines, the electrons go down the wire and they go into the copper. And at the copper, we have a copper 2 positive ion solution because, again, copper 2 nitrate completely dissolves in water. So copper 2 positive gains those 2 electrons and becomes copper solid. So at the cathode, this copper electrode will start to grow because the copper 2 ion will start to deposit on the copper electrode. And over here, the zinc electrode will start to shrink because it is going from zinc solid to zinc 2 positive ion in solution. So what are we seeing here? Well, we're seeing the same reaction we saw with just the one beaker, but in this one, we're getting work done we're getting work out of the electrons. We're getting the electrons to leave. We get them to heat a filament in a bulb up, and then we see the electrons go back. And to complete the circuit, that's why we have to have a salt bridge. If you don't have a complete circuit, then the charge is going to build up, right? Copper is going to go copper 2 positive to copper, and so there's no charge on this side. And the zinc, you're going to start, these electrons can't flow, and so this becomes zinc 2 positive, and then there's no, the copper, eventually there's no more electrons on the reduction side, so the copper remains 2 positive. So we don't see any reaction. So you got to have the salt bridge. Make sure that you have a salt bridge. Now, that's what it looks like visually. I want you to look at this. I want you to study it. Know what the anode is. Know what the cathode is. Know that oxidation occurs at the anode. Reduction occurs at the cathode. Know what the solutions are that these are submerged in. And know that we're doing work. Now, this is too bulky. This is too much writing, too much of an image. There is going to be a shorthand way to write this, and we're going to see that in a minute. All right, let's go back to some of the units that we're going to use in this class, or and especially doing the problem. So you have to know these units. So the first one is voltage. Voltage is potential energy. It's the potential energy between the reactants and the product. So just think of voltage as potential energy, and 1 volt equals 1 joule of energy per coulomb of charge. Now, you may have not heard of coulomb in a long time. The only time we've ever talked about coulomb up till this point is in Chem 170. We talked about the actual coulombic charge of an electron. So we've always said that an electron is -1 charge and a proton is a +1 charge. But remember, those are normalized charges, that the actual charge of the electron is not -1. It's the coulombic charge. It's -1.6 times 10 to the -19th coulombs. So we are going to be using coulombs, and if you plan to take physics, you're going to be looking at individual charges, and you're going to use coulombs as the unit of charge. Electromotive force. We don't generally say that. We say EMF, and EMF is how much force is pushing the electrons through the wire, and then that gets to be resistant. So that's what's happening in that light bulb. The tungsten filament's more resistant to electron flow then the wire, the copper wire, may be outside, and therefore it heats up, and therefore we get light out of it. So the more difference in voltage, the greater the pushing force, the greater the electromagnetic force, electromotive force. The current is the number of electrons that flow per second, so coulombs per second. And 1 amp is equal to 1 coulomb of charge per second. And 1 amp is equal to 6.242 times 10 to the 18th electrons per second. So you may want to, I'm not asking you to memorize that, but just keep in mind that 1 amp, because we use amp a lot when we talk about electricity, is a current. It is the flow of electrons per second, and 1 amp is 6.2 times 10 to the 18th electrons per second. So electrode surface area dictates the number of electrons that can flow. Larger batteries produce larger currents. So that's why we don't see a little small lithium battery in our cars. We need something that produces a large current so that we can crank the engine on the starter. Now, that doesn't mean that there's a lot of potential energy in a lithium-ion battery, but it gets to be real expensive to make one the size that we need to consistently crank a car. All right, so cell potential is the voltage difference, right? In a voltaic cell, it's the potential energy difference between the anode and the cathode. All right, so cell potential depends on the ease which the oxidizing agent releases electrons, and the oxidizing agent is reduced. All right, so what that means is the substance that's being reduced. Now, make sure you get this correct, because this is a common mistake. The substance being reduced is called the oxidizing agent. The substance being oxidized is called the reducing agent. So if we go back to this cell, the zinc is being oxidized. So the zinc, and this is the oxidation half reaction, but zinc is called a reducing agent. Why? Because the electrons that the zinc releases is being used in the other half reaction to reduce the copper 2 positive ion. So the zinc is the reducing agent. The copper 2 positive ion is called the oxidizing agent. Whatever is being reduced is called the oxidizing agent. And just think about it. What does a travel agent do? A travel agent assists you in your travel. So zinc assists the copper 2 positive ion being reduced by releasing 2 electrons. So zinc is the reducing agent, and copper 2 positive is called the oxidizing agent. The easier that those things happen, the more readily that happens, the more energy, Gibbs free energy for this will be negative, and it'll be spontaneous. All right? So these are really important definitions, and it's not just memorizing the definition, it's having a working knowledge so that you can apply these to problems. And I think that's a step right there a lot of students miss. It's all this new terminology, and it's not good enough just to memorize it. You have to understand how it works. That's why I stressed that reaction. So we have standard again. Standard electromotive force. Standard cell potential. So what is standard cell potential? It has to be 25 degrees Celsius, 298 Kelvin, 1 atmosphere for gases, and 1 molar concentration for solutions. And the sum of the cell potentials for the half reactions. All right, so the standard cell potential is after you add the half reaction cell potential, the half reaction potential for the oxidation, half reaction potential for the reduction. You add those together, you get the standard cell potential. All right, so this is what I was talking about. Instead of drawing that big fancy diagram that we saw, there is a compact way of writing voltaic cells. So here it is. You have the electrode always on the left, and that is where oxidation occurs. You have the electrolyte that's the solution that is around the electrode. You have the double vertical lines, which represents a barrier, a salt bridge. And so if you want to think of these lines as barriers, like here's the interface. If you look to the left, the electrode, this electrode is made of metal or gas or something. I mean, it's generally a metal. There's a barrier between that and the solution, the electrolyte. Then you have the salt bridge, which is a double barrier. It's a barrier on both sides of the half reaction. Then you have the electrolyte in the other container, a barrier, and then the solid electrode. All right? So make sure that you understand this designation here. So I'll give you some practice. So in this one, zinc is being oxidized. So here's my zinc solid electrode. Then there's an interface. And then we have the zinc 2 positive solution in here. All right. We have the salt bridge. There's my double barrier. We have the copper 2 positive ion solution in here. The electrolyte. And then we have the cathode, the copper solid. Make sure you understand this notation. I find a lot of students don't spend the time on it. But you can see it's much easier to write that than to draw a picture like this. So you're going to see that notation quite often. So typically an anode is made of metal that is oxidized. Metals tend to lose electrons. They want to be positive ions. By losing the electrons, they get a full outer shell of 8, that kind of stuff going on. Cathodes tend to be made of metal that will accept electrons more easily. All right? More easily. So another type of electrode that we use is an inert electrode. This is one that doesn't, it can go maybe oxidation or reduction, but the inert electron does not participate in the reaction, but just provides a surface for the transfer of electrons. All right? So it's not going to dissolve or gain. It's just to provide a place for electrons to transfer. All right, so let's look at this chemical cell. Electrochemical cell notation with an inert electrode. Okay, so here's what it looks like. We have iron. We have an iron 2 positive solution. And that could be iron 2 nitrate or something like that. So there it is. And so the iron is oxidized. So that's what we see here. The iron is oxidized into a 2 positive ion and a loss of 2 electrons. Over on the other side, the permanganate gains 5 electrons and 8 hydrogens from from an acid in this solution, and forms magnesium or manganese. Excuse me. Manganese 2 positive and water. So notice the cathode here is platinum, and platinum is not undergoing any chemical change. It's an inert electrode. It's there for the electrons to flow so that the electrons can react with the permanganate and form these products. And again, these products are not deposited on the platinum electrode. So this is what an inert electrode looks like. So how do you know that you probably have an inert system? Well, here's my anode. Here's my electrolyte. That part looks exactly the same. There's my salt bridge. But over here, this manganese ion is positive 7, or has an oxidation state of positive 7, and here it's positive 2. So here we can see that reduction is occurring. So that's going to give us an indication that the platinum, because it's not being reduced, is an inert electrode. All right? So that's the way to look for that. if you see multiple substances and of the same with a similar or a common ion, or common elemental with different oxidation states, then you probably have an inert electrode. All right, so this is really important, and I find a lot of students skip this part, and that is, how do we compare cell potentials? How do we know how much energy iron is going to release when it oxidizes to iron 2 positive? Well, just like delta H and delta G, since we're talking about energy here, since we're inside the universe, we have to have our reference point, a reference point where either the oxidation or reduction is equal to 0. And then, so if any oxidation or reduction is occurring, it is based solely on the other substance and not on another substance. So we have to have a defined electrode that we're going to say has 0 voltage. And we know that's not true, but we have to have a reference point, just like we have to have sea level. So the reference point for all electrochemical cells is the standard hydrogen electrode, and most of the time you'll see it SHE. So yes, we know that what's going on here is this hydrogen ion can be reduced to H2, so we could go from 2 hydrogen ions plus 2 electrons and reduce that to hydrogen gas. And you would see some bubbling occurring at this platinum electrode, and it would bubble up like that. But what we say is that the potential energy difference here is 0. All right, so that is what we make it. It's a definition that we have created and everybody follows. So now when I attach this electrode to any other half reaction, I can assign the voltage of that, or the potential energy, based solely on the other substance. That's why it's so important. All right, so it's the standard hydrogen electrode reduction potential is defined as exactly 0 voltage. So here's something we know. It's just like heat and everything else. Whatever the energy oxidized is negative the reduction, right? Whatever the reaction oxidation is, the reduction has to be opposite that. So here we go. We're going to take zinc at the anode. So we have a picture of it down here. Here's the reaction. Zinc at the anode is oxidized to zinc 2 positive, releases 2 electrons. We have that attached to a standard hydrogen electrode where reduction occurs. So when we measure the voltage, this is what the voltmeter would put out, negative 0.76 volts. And that tells us, that's what we would assign as the cell potential for zinc being oxidized. All right? So the current here is attributed by the zinc only. Even though we know hydrogen, yeah, there should be something here. We've assigned this 0 voltage. So we assign every bit of the voltage change to the zinc. And that's the way it works. That's the way we always do it. And then we can change out this reaction for anything we're interested in looking at, and we can figure out whether it's, what the voltage potential difference will be. Or either what the voltage will be or what the potential energy difference will be. All right, so you go, well, does that mean everything we do from now on has to have a standard hydrogen electrode? No. So once we have determined, we've put copper in here, we put zinc in here, compared it to the standard hydrogen electrode, we would find out that the cell potential for the oxidation of zinc is positive 0.76 volts. And the cell potential for copper to become copper 2 positive plus 2 electrons lost is negative 0.34 volts. So here's what we know. Zinc wants to give up its electron. Zinc has a positive voltage, positive potential. So that's kind of like the ball's up on top of the hill. When it rolls down, it's got the power. It's got the electromotive force of 0.76 volts. Copper, because it's a negative electromotive force, standard oxidation for this is negative 0.34. It's like it has to roll up the hill for this to happen, and that's not going to happen by itself. All right? But what happens when we put these two half reactions together and we have a salt bridge to separate the two half reactions? Well, because zinc wants to be oxidized, it will oxidize, and that's where the anode is. Zinc will oxidize. We call that the anode. Copper will be reduced because zinc's electromotive force is much greater than copper's electromotive force for oxidation. So because zinc is positive 0.76 and copper being oxidized negative 0.34, the copper reaction is going to go in reverse. The copper 2 positive ion will gain 2 electrons and become copper metal. So when we reverse the process, what happens to the sign on the, it's not now the standard oxidation, it's the standard reduction of copper 2 positive. That becomes a positive 0.34 volts. So if oxidation is negative 0.34, like they show here, all right, if it's negative 0.34 going in the forward direction, then in the reverse direction, it ought to be a positive 0.34. All right, and so if we add those two together, we will get the overall cell potential, which would be 1.10 volts, because you would add this plus the reverse of that, so the total cell potential of this would be 1.10 volts. And because it's a positive value, it's a spontaneous reaction, and we do have a battery here. We have a galvanic or voltaic cell. Voltaic's a better word. A galvanic, again, older term. I use the word galvanic still, but think of it as a voltaic cell. So how do you know what are the standard cell potentials? What are the standard oxidation potentials or reduction potentials? Well, we put them in a table, and we always say reduction. So even though over here these say oxidation, in reality what we do is standard reduction potentials. So there's a table, and I'm not asking you to memorize this table, but what I want you to get out of this table is be able to read it, be able to use it, and what you know is the higher the reduction potential on the table, the higher up it is on the table, the higher the standard reduction potential, the more likely that substance is going to gain electrons and be reduced, like the copper. The lower on the table, that means zinc 2 positive doesn't want to gain 2 electrons and become zinc. In fact, it wants to do the opposite. All right, so let me show you how this works. So here is the table, and it's pretty small. Let's see if I can I make that larger? All right, let's see if this will work for me. So there's copper 2 positive right here. All right. So let me see if I can I move that? Can I move that down just a little bit? All right. So let's look at this. Let's see. Let me get out my trusty pen. Ah, can you see that? Well, let's go back. All right. Let me move this around some. So I'm not going to get to use the pen here. So let me see if I can help you out here. All right. So you see copper 2 positive wants to gain 2 electrons, become copper solid, and it's a positive 0.34 volts. So that wants to happen. Copper 2 positive wants to be reduced. Below it is zinc 2 positive. So it's down here. Zinc 2 positive gains 2 electrons and becomes zinc solid. It has a negative standard reduction potential. So it doesn't want to happen. But if this reaction goes in reverse where zinc is being oxidized, that will make that a positive 0.76 volts. And so that reaction does want to happen, right? So as we go down the table, these substances are more likely, especially looking down this column on the right after the yield sign, these substances want to be oxidized. And the stronger a substance wants to be oxidized, they are called, or the easier a substance wants to be oxidized, if you want to think of it that way, the stronger the reducing agent. What is a reducing agent? A reducing agent is something that is oxidized. It releases electrons so that the other substance can be reduced. So the zinc solid, which is on the product side of this reduction potential, will oxidize and become zinc 2 positive and 2 electrons. So now it's being oxidized. And its electrons will then react with the copper 2 positive ion, which will form copper, and that's a reduction, and it's at 0.34. So we're going to be comparing the two half reaction potentials, and we're going to come up with the overall potential for the cell, the standard cell potential. All right, so we have the standard potential for the cathode, where reduction occurs, and we have the standard potential for the anode, where the oxidation occurs, and cathode minus anode will give us the overall cell potential, the standard cell potential. And we're going to see this work, all right? So here it is. Cell potentials are intensive properties of matter. Remember what cell intensive means. It doesn't matter how much you have. It doesn't matter how much zinc and copper 2 positive ion you have. The potential will always be the same. All right. Now, that is not talking about current. We're just talking about potential. Doesn't matter the starting, it doesn't matter how much you have, how big the battery is. The cell potential remains constant. All right, so here it is. Standard cell potential is equal to you need to know that equation, memorize that equation. This isn't hard. It's just like final minus initial, right? So we have an anode, we have the cathode. We're already doing the anode first. It releases electrons. They go into the cathode. It gains the electrons. Final minus initial, E cell potential. All right, so let's look at this problem here. Calculating the standard potentials for electrochemical cells from standard electrode potentials of the half reactions. All right, so right off the bat, what we notice is the aluminum is going from aluminum 3 positive. So it's being oxidized. Aluminum is the reducing agent. All right. What's being reduced? What is being reduced? Well, if I had to guess, I would guess it's the nitrogen. So let's figure it out. The nitrogen here has an oxidation number of what? Well, 3 times -2 for the oxygen is -6, and it's a -1 charged ion, so nitrogen here has a +5 oxidation number. Over here, we know that oxygen's -2, so nitrogen must be positive. Oops, +2. So nitrogen has been reduced from +5 to +2. All right, so that's what I need to look at. What are the, look at the tabulated values in that table that we just looked at and figure out what's going on. So aluminum's being reduced, aluminum's being oxidized, nitrogen and the nitrate is being reduced. All right, so we have our two half reactions. Now, here's something you got to watch again. Whatever these electrons have to be in agreement. Whatever's being lost here has to be gained here. All right, before you can add the two together. All right, so it's the E cathode. All right, so that is where the reduction occurs, is 0.96 volts, minus E anode, and the E anode, you're looking at the standard reduction potential. All right, so let's go back, because I find this is where students have a problem. And let's see if I can find it here. Right here. All right. So about midway down, you see nitrate, aqueous, gains 4 hydrogen ions and gains 3 electrons, and it's 0.96 volts. So that reaction wants to happen. It's going in. So I record that one, and then the aluminum. Go too far down. Let's see. There's the aluminum. So the aluminum, for it to be reduced, is negative 1.66. So we really know this wants to be oxidized. It wants to go the opposite direction. So we don't worry about the sign of this because it's going to be taken care of. Watch what happens here. When we put the aluminum of the reduction is negative 1.66, but it's cathode minus anode. So the negative and negative makes that a positive. So you just pull the values. You don't flip those in your head. You just know what's happening at the cathode is reduced. What's happening at the anode is oxidized. You record, you find the standard reduction potentials from a table. You plug in the cathode, you plug in the anode, and it's cathode minus anode. So it's a minus a negative 1.66. That's going to be a positive 1.66 plus 96, and we get 2.62 volts. So a positive potential, standard cell potential, all right, 2.62 volts tells me this reaction is spontaneous. This is a voltaic or galvanic cell. That's what you got to get out of that. Look at the table, and then there's another practice for you. All right, let's go. All right, so here's where I've been talking about it. Now we're actually going to predict it. All right, so for a spontaneous reaction to occur, the standard cell potential has to be positive. When the standard cell potential is positive, we know that the standard Gibbs free energy has to be negative. So they give us an example of a reaction we've already done over and over. Zinc being oxidized, copper 2 positive being reduced. It's got a standard cell potential that's positive, and it's also a spontaneous reaction because delta G, standard Gibbs free energy for this, is negative, and we know this is a battery. We've already seen it. If the standard cell potential is negative, then delta standard Gibbs free energy will be a positive value. Oops, there's a typo on this. Will be positive here. Let me write that. There's a typo on this slide. Shouldn't be negative. It should be positive here. All right. And so this reaction is going to be non-spontaneous in the forward direction. And so we would say this is not a galvanic or voltaic cell because it's not spontaneous. It's non-spontaneous. All right, so let's show you how this works. We've already done it, but we can do this. So we want to predict whether these reactions are spontaneous or non-spontaneous. All right, and they talk about you can sketch this out, you can write it out or whatever. But let's look at it. Iron is being oxidized, magnesium 2 positive is being reduced. And the other one, iron is being oxidized and lead 2 positive is being reduced. And the question is, will these be spontaneous reactions? And you go, I don't know. I can't tell. And so you go, how do you know? Well, you look up the standard reduction potentials for iron and magnesium. All right, so magnesium 2 positive being reduced, the standard cell potential is negative 2.37 volts. Well, that's not very good. It doesn't want to be reduced. All right, and the iron, for it to be oxidized would be a negative 0.45 volts. All right, and that's what has to happen. So you looked at the table, the standard reduction table. You flip the sign on the iron 2 positive being reduced and make it iron being oxidized, and that's a negative 0.45. If you add those two things together, you're going to get a negative value. For the standard cell potential is going to be a negative value, so this reaction is non-spontaneous. It's not going to happen. All right, so let's talk about it again. Look up the standard cell potential for magnesium 2 positive, or standard reduction potential for magnesium 2 positive. It's a negative 2.37. We looked up the standard reduction potential for iron 2 positive. We want the reverse of that reaction, so we change the sign and say iron's being oxidized. It's a negative 0.45 volts. And so when we add these two together, we get a negative value, therefore non-spontaneous. Delta G will be positive for this reaction. And the key is you have to look at this table. So let's see if I can do this and show this a little better. All right. So what I want you to look at here is we were looking at magnesium 2 positive. Magnesium 2 positive being reduced. All right. So there it is, negative 2.37 volts, about what? 6 up from the bottom. All right. In order for this reaction to occur spontaneously, the only so if that's going, what we would have to happen is something above it would have to be reduced, and something below magnesium 2 positive would have to want to be oxidized. Let's say it that way. Something below magnesium 2 positive would want to have to be oxidized. That would go the opposite direction, make that a positive value, and make the overall term positive. So because magnesium is here and iron is, let's see, it's way up. It's all the way up here, isn't it? Is that 2 positive? The 0.77, yeah. There's no way that happens. Iron wants to be reduced more. Iron 2 positive wants to be reduced more so than magnesium 2 positive. That's why it's a non-spontaneous reaction. So here's the other thing. You should be able to draw a picture of this. The anode. Magnesium's over here. Magnesium is being oxidized. It releases 2 electrons. The 2 electrons go down the iron electrode, and then they try to reduce the iron 2 positive. So I want you to be able to look at a chemical reaction, determine what the cell potential is based on the standard reduction potentials of each half reaction. If its standard cell potential is positive, then the reaction is spontaneous and delta G is negative. If the reaction is, the cell potential is negative, that means it's non-spontaneous in the forward direction, and delta G will be positive. And then being able to look at this balanced chemical equation here and translate it into a diagram like that. Or even better, be able to write this as you would have an iron electrode, you would have a barrier, you would have the electrolyte iron 2 positive, you would have a salt bridge, you would have, oops, I did this wrong. Yeah, let's do this over again. Magnesium, all right, and then you would have magnesium 2 positive, and then you would have a barrier. Let's make sure it's right. Yeah, magnesium is being oxidized. All right, and then we have the iron 2 positive solution, and then we have an iron electrode. So this is the shorthand way of writing everything that you see here. And technically, yes, you should put the concentrations. This is 1 molar and this is 1 molar. All right, you should write that as well. All right, so that's what I want you to be able to do. I want you to be able to look at a reaction, determine if it's spontaneous, which means it's a galvanic or voltaic cell. If it gives us a positive voltage and negative delta G, and be able to draw a picture of it and be able to write it in shorthand. All right, we'll stop here today. I think this is a good place to stop. It's a pretty long lecture, and then we'll work from there on the next one.